This is part 3 of the series Similarity, and in this part we're going to continue our discussion of similarity by presenting a description of how to determine if two polygons are similar. Based on our previous definition of similarity, we need to do two things. First, we need to determine that all corresponding side lengths are in the same ratio, that is, the corresponding sides are proportional. So let's begin with that, and we'll start with AB in the smaller figure, and we'll put down 4 is to 6 as 2 is to 3 as 4 is to 6 as 3 is to 4.5. This ratio simplifies to 2/3, 2/3, 2/3, and this ratio also simplifies to 2/3. Now we can clearly see that all these ratios are the same. But there's actually another way we can do this, and that is to verify the equality of cross products. So in this case, what we can do in instances where it's not quite so obvious as in this case whether or not these are true proportions, what we can do is multiply across the equal sign. So here we have 3 times 4, which gives us 12, and 6 times 2, which gives us 12. We can do the same with this. 6 times 2 is 12, and 3 times 4 is 12. And across here, we can say 6 times 3 is 18, and 4 times 4.5 is also 18. Now, it shouldn't matter whether the number comes up 18 or 12. The issue is whether the equality is maintained. Since 18 equals 18, this is a true proportional. Since 12 equals 12, this is a true proportional. And since 12 equals 12, this is a true proportional. So all these values are in proportion. I could also multiply these two together, and we would see 2 times 4.5 is 9, 3 times 3 is 9. So 9 equals 9. This and this are a true proportional. So that means these all 4 sides are proportional. So the second thing we need to determine is if in fact all the corresponding angle measures are congruent. And as we see here, they aren't, because this angle doesn't correspond to that. They're close, but not quite the same. This one doesn't correspond to this, this to this, or this to this. So you can see it's important that you compare both the corresponding side lengths and the corresponding angle measures. When we get into determining triangle similarity, our restrictions become greater and the possibilities fewer, so we won't have to make the same precautions. In fact, we're going to have a couple of theorems that we can rely on to determine if triangles are similar. But in the case of multi-sided polygons beyond 3, we have issues, as you can see, that we have to verify the angles, corresponding angles are congruent, and all corresponding sides are proportional. So hopefully this gives you a clearer idea of what's necessary to show that two polygons are in fact similar. Let's go ahead and move on to the next section. In this section, we come to the first of our theorems, and we're going to be talking about similarity of triangles. Now, this first theorem is actually also a postulate. It can be proven, so it's considered a theorem as well, but you can consider it a postulate that doesn't really require proof. And the reason is because it says if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. And we know that if two angles of one are congruent to two angles of another, then by the third angle theorem, we know that these third angles must be congruent. And since angles determine shape, we know that these two triangles must be similar. So let's go ahead and take a look at that in a little bit greater detail in a dynamic picture. Here we have two triangles, and we have angle A is 90 degrees, angle beta is 90 degrees, or angle F, and angle C is 39.81, and G is 39.81. By the third angles theorem, angle H has to be congruent to angle B, and so if we bring those two angles back in, we can see that they're both 50.19. Now, the idea would be that these two triangles are similar, and what that would mean then, the corresponding side lengths would have to be proportional. So let's go ahead and bring in FG and AC, and we can see our ratio 12:6, which is 2. So this shape should be twice the size of this, which means each one of these sides is half the length of this side. So let's bring back HF and AB, and we can see that relationship is maintained. And finally, HG and BC. It's a little odd, but 7.81 times 2 would be 15.62. So we can see that all the corresponding side lengths are in the same ratio. So in fact, with two congruent angles, these triangles become similar polygons. And just to verify one last thing, let us pull in a polygon, and let's go ahead and create a similarity transformation that maps this one to this one. So the first thing I'll do is translate this polygon up to the other one. So we translate it up, and then we're going to go ahead and dilate it, and we can see that we've created the same triangle. So there is a composition of similarity transformations that maps this to this. So by angle-angle similarity, these two triangles are similar. Let's go ahead and use this idea in a quick example. In this example, we want to determine if these two triangles are similar. So here we have two right triangles because of these right angles. This angle is 34 and this is 56. Since these are right angles, the two acute angles must be complementary, which means they add up to 90 degrees. So what do we add to 56 to get to 90? 34. So the complement of 56 is 34, and the complement of 34 is 56. So by angle-angle similarity, we have two congruent angles, and therefore these two triangles are similar. So let's try another example. In this example, we have two embedded triangles. We have triangle SQT embedded in triangle PQR. Now we've seen several examples like this in the past, and we know that angle Q is being shared between the two triangles. So angle Q is congruent to itself by the reflexive property of angle congruence. And since we have angle QST is 76 and QPR is 76, we have similar triangles by angle-angle similarity. This angle and this angle and this. So these triangles are similar. Let's go ahead and work yet another example. In this example, we're going to have to dig a little bit deeper, but not too far. We can see that angle LNM and ONP are vertical angles. So these two angles are congruent by the vertical angle congruence theorem. We have two parallel lines here, LM and OP, and we know that if two lines are cut by a transversal, then the alternate interior angles are congruent. So we know that angle OPN is congruent to PLM, and so we have these two angles congruent. Therefore, by angle-angle similarity, this triangle LNM is similar to triangle ONP. Let's try one more example. In this example, we have a representation of a building and a 6-foot pole. And these are rays of sunlight coming from the sun, and because of the distance from Earth to the sun, these rays are considered parallel. So these two lines are parallel, and we have created two separate triangles here. And we have right angles in these two positions. So this pole is perpendicular to the ground, and this building is perpendicular to the ground. The building is casting a shadow of 642 feet, and the 6-foot pole is casting a shadow of 9 feet. We want to determine how high is the building based on these measurements. Now, for the purposes of this exercise, we're going to disregard the curvature of the earth, and we're going to assume that the ground is straight and level, and so perfectly straight across here. Which means that if we have two parallel lines cut by a transversal, then we have corresponding angles here that have to be congruent. Therefore, since this is a right angle and this is a right angle, and these two angles, these corresponding angles, are congruent, then we know that this triangle and this triangle are similar by angle-angle similarity. Therefore, we know that we can set up a proportion relating these two sides to see if we can find the measure of x. Therefore, we're going to use this side, x, is to 6 as, go back to the original triangle, 462 is to 9. We only have to solve for x, so we multiply by 6, x equals 462 times 6 over 9, and that's going to equal 308. So I hope that gives you an idea of how to use angle-angle similarity. So let's move on to the next idea. Now we come to the second of our similarity theorems, and this is the side-side-side similarity theorem. Now what the side-side-side similarity theorem says is that if the lengths of the corresponding sides of two triangles are proportional, then the triangles are similar. Now this theorem should not be confused with the side-side-side congruence theorem. What we're talking about here is proportionality and not equality. So if we can state that the ratio of AB to DE is equal to the ratio of BC to EF, which is equal to the ratio of AC to DE, then these two triangles must be similar.